Well, there are a number of relationships between the group velocity and the phase velocity that you sometimes see. And so let's take a look at how those are arrived at and what they are. As we saw in the previous segment, we have two different velocities in general for superpositions of waves. One is the phase velocity, which is just omega over k, and the other is a group velocity, which is d omega dk. But there's some other common forms that are sometimes useful, primarily experimentally, but I've seen them used in other contexts as well. From equation 1 up here, you can rearrange that to see that omega could be written as Vp times k. And then you could use that in equation 2. Just plug in for omega this Vp times k. And then take the derivatives, realizing that Vp may actually depend on, the phase velocity may actually depend on k as well. And so it's really just the product rule. So take the derivative of that, I'll take the derivative of k, which is just 1, so Vp times derivative of k, which is 1, plus k times the derivative of Vp with respect to k. And so we get the first relationship that sometimes is useful. Again, you note that the k, v, g, and Vp are not the same in general. They will be the same if there is no dispersion. And that's often the case in terms of the vacuum, for instance. As far as we know, the phase velocity omega over k is the speed of light, and that's just a constant and does not depend on the wavelength or the wave number. And so this term vanishes, and in those contexts, the group velocity is the same as the phase velocity. Well, we also very often have written things in terms of the index of refraction. Just to remember, that was c over the wave velocity. And as I've said, the wave velocity is the phase velocity. So indices of refraction are really c divided by the phase velocity. And one can use that. Oftentimes, the index of refraction depends on the frequency wavelength of the light that you're using. And so we can differentiate that. Of course, the speed of light in the vacuum doesn't, is just a fundamental constant. So if I take the derivative of the phase velocity with respect to k, it's just whatever the dependency is using the chain rule on and the index of refraction. And so one differentiating this gets a c is just a constant, minus 1 over n squared times dn dk using the chain rule, assuming that k could depend on the dispersion and have some wavelength dependence, which we know it does in general for most media, but not for the vacuum. And you just plug that in to the equation above, dvp dk, and replace it with this. You get this expression. And then you can manipulate that a little bit. The minus sign can come out front, so you have ck over n squared dn dk. And you can rewrite it as c over n, k over n. Mainly because we know that the phase velocity is just c over n up here. Okay? And so I'll replace this c over n by the phase velocity, and then factor out the phase velocity. And so you find that the group velocity is related to the phase velocity, depending on, the big factor is this one usually, and then you have a dependence on k and the index of refraction, and the dispersion, how n varies with how the index of refraction varies with the wave number. So that form is sometimes used experimentally. A more common one experimentally is one in terms of wavelengths, and just to recall, k is 2 pi over lambda, so lambda is 2 pi over k, and I can differentiate dn dk, again using the chain rule. It's going to be the derivative, the change of n with lambda, d lambda dk, but this is 2 pi over k, and if I take the derivative of 2 pi over k, that gets me a minus 2 pi over k squared, and rearranging one gets this, and then plug that in up here. So you get one of the k's will cancel. So one of the k's cancel, minus minus is a plus. You have a 2 pi that comes out. You still have a k in the denominator, and then this overall factor of 1 over n, but now I've got n in terms of lambda. And then finally, just plug in what the k is. K, remember, is 2 pi over lambda, so the 2 pi's will go out and the lambda will flip over on top. And so this factor here simply is, well, this is just lambda, right? 2 pi over k is lambda. And lambda is 2 pi, or k is 2 pi over lambda, so 2 pi over k is lambda. But in any event, use the lambda k relationship and you get to this form. This is actually the form that experimentalists seem to use most commonly. And the reason is they tend to think of the index of refraction, and that's the way I do too, is something that depends on the wavelength of the light. If we have a dispersive media, so if the wave velocity of red light is a little bit different than the velocity of blue light, then you see this prism phenomenon going through of light propagating through interfaces, and you get a phenomenon known as dispersion. So when the index of refraction depends on lambda, then it's generally a very weak function of lambda. You have to make fairly precise measurements, but in most media, you have slightly different velocities for the electromagnetic waves depending on the wavelength, and so you see this relationship between the group velocity and the phase velocity used a lot, particularly in terms of experiments.